So welcome to our last part of lecture 29. In this part, I want to talk about some consequences of having the Grahm-Schmidt theorem. And so they're going to be very useful to kind of allow us to just make kind of some general statements. Okay, so the first one, and I think one of the more useful one, is that whenever you have a finite dimensional inner product space, it actually has to have an orthonormal basis. So you can find an orthonormal basis. And why is that? Well, what the proof is actually very simple, all right? What you do is you just simply apply the Grahm-Schmidt to any basis of V. Take your finite dimensional vector space, it has a finite basis, so you get a bunch of linear independent elements, apply the Grahm-Schmidt, you get a new set of elements that are linear independent that have the same span as the original vectors, but that means that that new set of orthonormal vectors is actually a basis. Okay, so that's great. Any inner product space has an orthonormal basis. The other useful fact that we have is that whenever you have an orthonormal set of vectors, it may not be big enough to be a basis, but you can actually extend that to an orthonormal basis of V. Okay, and why is that? Well, let's say that E1 through EM is orthonormal, and you can take any set of linear independent elements and you extend it to a basis. Okay, the problem is when you extend to a basis, these new elements that you've added may not have the property, may be destroying the orthonormal property. So these vectors at the beginning have the orthonormal property, but these don't. But now what you do is apply Grahm-Schmidt to this list. Okay, and by construction, okay, so the way that the algorithm works, Grahm-Schmidt will return, now I know I'm kind of skipping some details, but it will actually return E1 through EM, and then it will continue to make an orthonormal set from there. So basically what this is saying is if we go back to the Grahm-Schmidt theorem, and we know some facts about the first couple vectors saying that it's orthonormal. When you feed it into this process, if your first vectors are orthonormal, it will actually just return back those vectors that you started with. So the procedure doesn't actually change vectors that are orthonormal. It's only when you get to a vector that kind of destroys the orthonormal property that it tries to fix it. Okay, so that's kind of one way to think about what the Grahm-Schmidt process is doing. So like when we feed this in, it's saying, oh, these guys are all orthonormal, so I don't need to change it. Oh, F1 destroys my orthonormal property. I'll fix it. And it will give you a new G1 that allows you to build up the orthonormal basis. Okay, and another useful fact here, and I won't give the whole proof, I'll just sketch out the idea, is suppose that we have a linear operator and V has a basis such that the associated matrix is upper triangular. Then you can actually prove that V has an orthonormal basis such that the matrix is upper triangular. And the idea is to apply the Grahm-Schmidt to the given basis, right? So you apply the Grahm-Schmidt to the given basis, you get an orthonormal basis, and then show the new orthonormal basis has the property that the associated matrix is upper triangular. Okay, and you go and use some of the previous results that we had about when is a matrix upper triangular. Okay. So probably one of the last, well, there are many useful consequences, but the last useful consequence for today's lecture is Shures Theorem. And Shures Theorem says that if T is any linear operator and if it's a complex and V is a vector space over the complex numbers, then there's automatically an orthonormal basis of V such that the matrix MT is upper triangular. Okay, and why is that? Well, by theorem 527 in chapter 5, which we talked about, over the complex numbers, there exists a basis such that the matrix MT is upper triangular. So we can make an upper triangular basis, but then now apply the previous result. Okay, so now apply the previous result. Because the previous result says once you have something upper triangular, you can make an orthonormal basis from that. Okay. Now in the textbook, I should point out, they only do Shures theorem over the complex numbers, but it actually holds over the real numbers, but you need a different approach, and we won't do that in this course. Okay, but you can maybe, if you're interested, you could go look it up. Okay, so there's a bunch of things that we've learned today. Kind of the big ideas are orthonormal sets and orthonormal bases, so know those definitions cold. We've seen the Grahm-Schmidt process for any inner product space, and then we saw some useful consequences of this, one of the things namely being Shures theorem, but the other one I would say is that any inner product space has an orthonormal basis. So in the next class, we'll continue up our look at section 6b, and we'll also do some examples of some of this material and the material from the next lecture. And that's it for today. Have a great day.